This is problem 87 from chapter 4. First thing we need to do is predict the products of this reaction that occurs between potassium hydroxide and nickel 2 sulfate. We figure out those formulas based on the charges of the ions. We then balance the equation, and that's part A. Part B, is figuring out which one is the precipitate, and we figure that out based on solubility rules. And hydroxide is a bad guy, nickel is a nobody, so that's our insoluble product, that's the solid. Potassium's a good guy, he's a groupie. And we have sulfate, there's our pig. It's not a dancing pig because it's not Cabaster Pub Hog 2, so potassium sulfate is soluble. In order to find the limiting reactant, which is part C, we've got to convert to moles so that we can use the coefficients of the equation to help us figure it out. Well, you remember that molarity times volume, it gives us moles. So we have 0.02 moles potassium hydroxide. We do the same for nickel sulfate, and we find that we have 0.03 moles of nickel sulfate. Now, some of you are going to be able to see right away which is the limiting reactant, but I'm also going to show you how to make that calculation and draw the conclusion based on your calculation. So if we have 0.02 moles of potassium hydroxide, we're going to multiply by a mole ratio of 1 mole of nickel sulfate for every 2 moles of potassium hydroxide. That came right from the balanced equation right up here. We carry out that calculation, and that's going to tell us how many moles of nickel sulfate will react with 0.02 moles of potassium hydroxide. And that easy math, we find that it's 0.01 moles. Well, we have more than 0.01 moles, we have 0.03. So that tells us nickel sulfate is going to be the excess reactant, therefore potassium hydroxide will be the limiting reactant. Now, because potassium hydroxide is the limiting reactant, it's going to control everything else. So we bring that knowledge into part D when we're asked how many grams of precipitate form. Well, potassium hydroxide controls that. Once we run out of potassium hydroxide, the reaction stops. So again, it's a simple mole ratio. We have 1 mole of nickel 2 hydroxide for every 2 moles of potassium hydroxide. Again, those numbers came right from the coefficients of the balanced chemical equation. We're going to use the molar mass of nickel hydroxide, and we're going to calculate the number of grams of precipitate that form. So we're going to start part E by looking at the spectator ions. We're going to look at potassium hydroxide first because it's not involved. We know how many moles of potassium hydroxide we have, which is 0.02, and we can use a mole ratio from that chemical formula that tells us that there's 1 mole of potassium ions for every 1 mole of potassium hydroxide, and so we can say that we have 0.02 moles of potassium ions. Well, those aren't going anywhere. They don't get caught up in the precipitate. They're still floating around in the solution. So we have 0.02 moles of potassium ions floating around in solution. But now our solution has a volume of 300 milliliters. So to find the molarity of the potassium ions, we take the number of moles of potassium ions, divide it by the volume of the solution. That's 100 milliliters from the potassium hydroxide and 200 milliliters from the nickel 2 sulfate. And we get 0.0667 molar potassium ion concentration. It's the same process for the sulfate ion. We have to find out how many moles of sulfate ion we have, divide that moles by the volume of solution, which again is 0.3 liters, and you should come up with 0.100 molar, or moles per liter, of sulfate ion. So now the ones that are a little more difficult, we're going to deal with the ions that are involved in the precipitate. Although the first one we're going to deal with, the hydroxide ion, is probably the easiest one of all, because it comes from the limiting reagent, so all of it gets consumed and it goes into the precipitate, it goes into the solid. And we know that insoluble compounds don't dissociate at all, so we're not going to have any hydroxide ion in solution at all. So the molarity of hydroxide ion in solution should be 0. Now calculating the nickel ion concentration is probably the most involved one of all. But when we look at part C, we found out that we're going to use 0.01 moles of nickel sulfate. Well, we had 0.03, we used 0.01, and all of that nickel that got used went into the precipitate, but we have 0.02 moles of nickel ions left over. And so dividing that number by the volume is going to give us the concentration of nickel ions once this reaction is done.